Hi, my name's Tom Heffel, and this channel is all about helping students learn chemistry. In this lesson, we're going to talk about the introduction to thermodynamics. And these bullet points are the things that we're going to be discussing in this video. And this video really is all about trying to talk about energy in general terms. And then in later videos, we're going to go into specifics of what's required when it comes to chemistry and energy. So let's go ahead and get started with the first law of thermodynamics. There's going to be 3 of them throughout this unit, and we're going to talk about the first law, which I think a lot of people already know, and that's that you can't create or destroy energy. Energy is always going to be conserved through its transformations. When we're talking about energy, maybe it's a good idea that we define it. Okay, so energy is the capacity to do work, okay, or transfer heat. Okay, and that's going to come back when we talk about this internal energy equation. So once again, okay, the definition for energy, okay, is the capacity to do work, okay, or transfer heat. Now the units on energy is going to be the joule. Now when we talk about the joule actually consists of other units. It consists of the kilogram and meters, and it's going to be divided by seconds. Okay, so kilograms times meters squared divided by seconds squared is actually the unit for the joule. Okay, now there's a couple equations that you've already probably discussed in previous science classes. Maybe something like kinetic energy, which is 1/2 times mass velocity squared. Okay, this mass, it actually has to be in the unit kilogram, and this velocity is typically in meters per second. Of course, when you square that, you end up squaring the meters and the seconds, so it comes out to be kilograms times meters squared over seconds squared, which is the unit for the joule. Okay, this is also true for potential energy. Maybe from a previous science class, you remember that potential energy is the mass times the gravitational force and also how high the object is. The higher the object, the more potential energy, okay? But that mass has to be in kilograms. The gravitational pull is going to be in the unit of meters per second squared. That's an acceleration unit, okay? And then the height is going to be in meters as well. So you got meters times meters, which is meters squared, times kilogram in the numerator, and you still have seconds squared in the denominator. So once again, these are the units that make up the joule. And it's really important that you know that, because if I were to give you a kinetic energy problem and the mass was in ounces, well, you wouldn't be able to plug and chug, okay? You'd have to take those ounces and convert them into kilograms, okay? Because it's only equal to a joule if the mass is in kilograms. Same thing for velocity. If I gave you a kinetic energy problem and the velocity was in miles per hour, you would have to convert that over to meters per second, because miles per hour squared is not part of the unit of a joule. So you got to be really careful with your units when we're trying to figure out how much energy is present in these different situations. So another thing that I'd like to talk about briefly is the relationships between kinetic energy and these variables. Okay, obviously this is a direct relationship. As the mass goes up, the kinetic energy goes up. As the velocity goes up, the kinetic energy goes up. And that would be true over here. As the mass, gravitational force, or the height increases, you're going to have more potential energy. So as one goes up, the other goes up, and we call that a direct relationship. But sometimes I do like to talk about this guy right here. Okay, what if we doubled the velocity? What would happen to the overall kinetic energy? Okay, well, I got a sample problem here for us to look at, and that is something that looks like this. Let's say we had an example where the mass of the object is 1.2 kilograms, and this 1.2 kilogram object is moving at 5 meters per second. Okay, well, if you plug this into the equation of 1/2 times mass velocity squared, and you figure all this out, okay, it'll end up becoming out to 15 joules. Now, the question is what if I doubled this? Well, some people think that if you double the velocity, you double the kinetic energy, and that is the wrong answer, okay? So let's go ahead and kind of figure out what would happen if we doubled the velocity. Instead of 5, okay, what if we put 10 meters per second? That would be doubling it. Well, 1/2 times 1.2 times 10 squared is actually going to come out to 60 joules. Okay, so from 15 to 60, that is actually a factor of 4. Okay, that's 4 times more energy when we double it, and that's because this velocity is squared. So if we doubled this, well, 2 times, or not times, but to the second power would be a factor of 4. If we tripled this, well, 3 squared would be a factor of 9, okay? So depending on what happens here will depend on what's going to happen over here. So for everything else, if you doubled this, this would double. If you doubled this, this would double. If you doubled this, this would double, because there's no squaring, okay? But because of the squared here, you have to really pay attention to that. So if I doubled the velocity, it's going to be a factor of 4 in which the kinetic energy is increased. So just be on the watch out for anytime a unit has an exponent on it, you need to understand that relationship. Yes, as one goes up, the other one is going to go up, but it's not going to be like if you double this, it's going to be double that. Okay, so let's get to the internal energy equation. Okay. The internal energy equation is equal to Q, and this is the way I do my Q, so you don't have to draw it this way, but it's equal to Q plus W, where Q is actually heat, okay, and W is going to be work. And this really brings us back to the definition of energy, okay, back to our definition. Remember, it's the capacity to do work or transfer heat, okay? And what internal energy is, if I could give you like an analogy of it, it's kind of like a bank account where we don't know the balance, okay? And so I'm going to write that down. It says as an example, so i.e. that bank account, okay? And I'm going to give you an example. Let's say I have this bank account and I don't know the balance, because that's kind of like what internal energy is. But if I know the deposits and withdrawals, I know how the balance is going to change. For example, if I have this bank account of which I don't know the balance of, but if I deposit $10, okay, and withdraw $5, well, I know that the change of the balance is going to go up by $5 because I put $10 in, but only took $5 out. That means that bank account balance increased by 5, okay? And that's kind of like how internal energy works, okay? We don't know the exact internal energy of a particular system, okay? But if we put work into it and some heat into it, and then we take some work out of it and we take some heat out of it, we know the change of that internal energy, okay? And that's kind of like what delta E is all talking about. So delta E, once again, is this idea of internal energy, or really the change in the internal energy, because remember, our delta sign is the change, okay? And I have this example. It's not a perfect example, but I think it'll kind of help you out with what we're talking about, okay? So let's say I have this hot plate, and this hot plate has a beaker of water on top of it, and we're going to put 100 joules of electrical work, because that's the way hot plates work, right? You plug them in, you turn the dial on. When you turn the dial on, electricity comes in. We'll call that electrical work, okay? So it's going into the hot plate, okay? I turn the dial on, and all of a sudden it's going to produce a certain amount of heat. And let's say this heat that comes out is 90 joules, okay? Well, we got this idea of system versus surroundings. And what we're going to talk about first is the system of the hot plate. and we're going to talk about the change of internal energy of that hot plate. Okay. Now, when it comes to anything, if we're talking about a system, any system, in this case, it's going to be the hot plate system. If something goes into the system, we want to make sure we signify that with a positive sign. So if this could be heat going into the system, it could be work going into the system, but if it's going into the system, it's going to be a positive sign, okay? And the exact opposite is true, okay? If the system does something to what we call the surroundings, so anything that's not part of the system is what we call the surroundings. And if the system is doing something to the surroundings, okay, we're going to use a negative sign. So if the system releases heat, okay, we're going to make sure that heat's a negative sign. And if the system releases some work or does some work onto the system, that's going to be a negative sign for the system. So if something goes into the system, it's positive. If something leaves the system, it's negative, okay? And what we're going to try to do is try to figure out the amount of internal energy for this hot plate. So we're going to be talking about the hot plate system, okay? So the change in internal energy is equal to Q plus W, okay? Let's talk about the Q part first, okay? That's the heat flow, okay? Well, it looks like when it comes to heat, it looks like 90 joules of heat is leaving the hot plate, okay? And remember, if something's leaving a system, we give that a negative number. So we got negative 90 joules. And we got to talk about the work. We got 100 joules of electrical work, and it looks like it's going into the system. And if something's going into the system, we got to remember that that's a positive sign. So that's going to be positive 100 joules. So the change of the internal energy of this particular system when the hot plate is on, for the example that I have up here, negative 90 plus 10 joules is going to say that the hot plate system has a change of internal energy of 10 joules, okay? Now, the whole idea of this, okay, is to make sure you really keep track of your positives and negatives. If you're in math class and you just make a mistake, oh, it should have been a negative 10 instead of a positive 10, and your teacher might just do like a -1, okay? But in science class, in thermodynamics, in chemistry, messing up a plus or a negative sign just a little bit, it's a big deal because you actually have the problem exactly backwards, okay? So it's going to be a lot of points when it comes to thermodynamics. It's not going to be like a -1 in math class. It might be like -50 or 75% of a particular problem. So you really, really have to keep track of, are things going into that system or are they leaving that system? And those signs become incredibly important, okay? So if we changed our idea of the hot plate system to the beaker system, let's talk about what's happening to the beaker. Will the beaker have a change in internal energy? Okay, let's talk about the heat flow first, okay? Well, the heat flow here, the heat's not exiting the system, it's going into the system if our system is now just the beaker of water instead of the hot plate, okay? So the heat flow for the hot plate, okay, was negative 90 joules because it was leaving that system. Well, it's for our system of the beaker, it's going into the system. So that's going to be a positive 90 joules, okay? Now, there's nothing talking about work being done on the beaker or the beaker of water doing any work. So that's going to be 0 joules. So the change in the internal energy for the beaker is going to be a positive 90 joules. Okay, that's kind of what's happening with the beaker of water system. So another thing that we have to do in chemistry is we have to focus in on what is the system and what is the surroundings. So when you're reading the prompts in your homework, okay, you have to make sure, hey, what is our system? Is it the hot plate, okay, or is it the beaker of water? Because the way you define your system will depend on how your change in internal energy is going to be, okay? The last thing that we need to talk about is this idea of state function, okay? State function is where the path does not matter. So the idea that I have here to really get you to understand what a state function is this idea of displacement versus distance traveled. Okay, so we're going to write that down. Displacement versus distance traveled. And what I have here is what I'm going to call position A and position B. Okay, and we're going to have two scenarios. Okay, scenario number one is where a person simply moves from position A to position B in a straight direction. Okay, and let's say that distance there is 1 meter. Okay, between A and B. However, scenario two is going to be a different situation. It's where the person's going to walk this way and then maybe all the way around. But they do end up at position B. Now, when they did this, maybe they took about 10 meters to do that. Okay, so the displacement in both situations is going to be 1 meter. Okay, it doesn't matter, the path that you go for displacement. However, distance traveled would be different. Okay, the way I got from point A to point B in scenario one is I only traveled 1 meter. Okay, now in scenario two, I traveled 10 meters. Okay, so the path matters for distance traveled. So distance traveled is not a state function. And that's because the path matters. Okay. When it comes to displacement, though, okay, the difference between point A and point B is 1 meter. It doesn't matter if I go here to here or if I take this long path. The difference in their positions is exactly 1 meter, and that's how displacement works. So displacement is a state function. And an easy way that you can tell your state functions a lot of times is when there's a delta sign, okay? And you're going to see some state functions in this unit. Yeah, we're going to start out with delta E, but we're going to maybe talk about delta H, delta S, and delta G, okay? Which is, hey, we have this position in the beginning, we have this position at the end. What's the change in those positions, okay? Those things are state functions where the path doesn't matter. It doesn't matter if you go up, down, up, down, up, down. All that matters is where were you in position one, where are you in position two, and what's the difference between those positions. That is what a state function is. And I'm using displacement versus distance traveled to talk about it because that's a little bit easier than talking about delta E, delta H, delta S, or delta G. But fundamentally, okay, it's the same idea, okay, where the path does not matter. If you found any of this information helpful, please give it a like or subscribe. Leave a comment because that really helps us push out the information to other students that are really interested in learning chemistry.